This video is all about geometric probability. The first thing that we want to take a look at are the formulas that we've been using and kind of refresh our memory with them. So parallelograms, you do base times height. Square, you can also do base times height, or you can do side squared. Same thing with a rectangle, you can do base times height. For a triangle, it's 1/2 base times height. For a rhombus, it's 1/2 d1 times d2, so you're multiplying the diagonals together and then taking half of that. For a trapezoid, it's 1/2 height times base 1 plus base 2, so you're adding the two parallel sides together, multiplying it by the height and taking half of that. For a circle, our area is pi r squared. And we're going to use a few of these formulas in order to figure out our geometric probability. So let's take a look at a simpler problem. Given a line segment, we've divided it up into 7 sections, right? So we have A through G, and they're given the numbers 0 through 6, right? So we want to figure out what's the probability that a point chosen at random would be on, for the first one, CE, so that segment. If we take a look, CE is this piece here. Now, for that section, that's only 2 segments long, whereas the entire thing is 1, 2, 3, 4, 5, 6 segments long, or 6 sections long. Right? So our probability that a point would land randomly on that section for CE is going to be 2 over 6, which we can then simplify to 1/3. The second one says CF. Well, that's a little bit longer. So now we're looking at from C to F, which is 1, 2, 3 sections out of 6. So that's going to be 3 out of 6, which simplifies to 1/2. And of course, we have to get into our shapes as far as geometric probability goes. Things like this might happen when you're aiming for a certain section of a dartboard, or you're trying to get a beanbag into one of those cornhole games, right? Things like that. We could probably do this while playing Can Jam, any of those. So what we're going to do is, the first problem says we want to know what's the probability that your point chosen at random would be in circle B. Okay, so we want to basically figure out the area of circle B as well as the whole rectangle. So you can even look at this as a beanbag toss kind of cornhole game, right? Circle B might be the hole that you're aiming for. So what are your chances of getting into the hole? If we take a look, let's find the area of our circle first, right? So we're going to take pi times 3 squared, because 3 is our radius right here. So that's pi times 9. So our area is 9 pi. Now, of course, our rectangle does not deal with pi. So at this point, we might as well take 9 pi and get it to an answer to the closest 10th, right? So we can say our area here is going to be 28.3. All right. Now, area of rectangle, well, that's base times height. There's our 8, and there's our 10. So we're going to do 8 times 10. Our area is therefore 80. And then what we want to do is we want to figure out the chance of getting in the circle versus the whole space. So we want to take 28.3 and divide it by 80. So if we take 28.3 and divide it by 80, we get 0.354. Now that, if we change our probability into a percentage, you have a 35.4% chance of getting into the circle. Right? So now, what's the probability that a point chosen at random would be in the shaded region? Okay, now, the shaded region has a section cut out of it. It has that circle cut out of it. So we want to take 80 minus 28.3 and figure out what that is, so that way we can do the same ratio that we just did before. So if we do that, 80 minus 28.3 is going to give us 51.7. So now our probability is 51.7 over 80. So 51.7 divided by 80 is going to give us 0.646, or if we wanted a percentage, you have a 64.6% chance of hitting the shaded area instead of the circle. So, the last problem that we're going to take a look at as far as geometric probability goes is the area of a sector. Okay, now for a problem like this, it's kind of nice because you have already, I'll kind of zoom in on this one, you have our angle measures, all central angles, right? Since our vertex is at the center, we have our angle measures for all of our different sections. We also have the diameter for our circle. So we want to find the area of sector 2. So we're going to use the formula that we have at the top there. We're going to fill in some information. Right? So the area equals the central angle for sector 2, which is 70, divided by 360, times pi r squared. Well, the diameter is 12, so our radius is 6. Okay, so now, if we simplify this into little teeny tiny baby steps, I have 70 over 360 times 36 pi. Now, I am a fan of leaving pi in my final answer because if you can do that, it's easy enough to plug in 3.14 when you're done. So if we take 70 and divide it by 360 and times that by 36, we're going to get our area to equal 7 pi units squared. Okay, so now you could go ahead, knowing that area, you could find the area of the circle and figure out the probability of a point landing in sector 2 or a point not landing in sector 2 using the same process that we did in the previous slide.